Hi, and welcome to this next video on recurrent neural nets, where we discuss how to train them. Again, this video assumes that you've already watched the videos on how to train normal neural nets. And if you haven't, then maybe at least you have read about it somewhere else. Okay. So what we looked at in the previous video was, I guess, we motivated these recurrent neural nets for machine learning on sequential data with this example of perhaps predicting stock prices of Google, where the idea is that you have this sequential data, you have the stock prices every day, maybe you even have some more features available, and the goal is to predict the stock price tomorrow. Now, what we introduced was this idea of a recurrent neural net, where we also went through this idea that we have all this data for all the time steps, and the idea is that in every single time step, we feed in these features that we have available, say the stock price of Google, the inflation, stock price of Apple, feed them into input neurons here at the bottom of the neural net. And then we have a standard feed-forward neural net. We pass it through the network. It produces some output for this step, but also a state that we then feed in as input to the next time step when we move on to the next feature vector. Right, so watch the previous video if this is unclear. Now, the idea is that we want to train such a recurrent neural net. Let's at least first of all talk about what does our training data look like. Let's just have some notation for that. So the idea is, the way we're going to write it is that we have features available. If we have a sequence of data, these features consist of feature vectors x1, x2, xt, where each of these feature vectors is a d-dimensional vector, right? So we measure d different properties for every single time step. So the whole sequence is described by a whole number of different feature vectors, each of d features that we have. So xt will denote the feature vector for step t of the sequence, right? So for perhaps such a feature vector could contain the Google stock price at this step t, the current inflation at step t, the Apple stock price at step t, just to give an example. Okay. The labels now for such a task, at least in the most general setup, is that we also have a label for every single step. And this is in some sense the target label that we want to predict at the end of step t. Right, so these labels could be just numbers, -1, 1 for binary classification type problems. Could also be a one-hot encoded vector if we're doing classification into k classes. It could also be just a value if we're doing a regression type problem. Okay. And for regression type problem, why these labels could be the stock price of Google at step t+1, which is what we want to predict, what we want to predict after step t. Right, so this could be just a real value. Right, so nothing special here compared to ordinary supervised learning, only that now a sequence is described by a whole collection of feature vectors and labels. Okay, so that's just a bit of notation. So think of this, just the labels are what we want to predict using this model. And this is also what we want to predict after the end of processing our whole sequence. Okay. Now, just to try and talk about how we train these recurrent neural nets, I'll try to just simplify this architecture just to make the notation and the figures a little bit easier, right? But it generalizes just as easily to more complicated structures of these recurrent neural nets. So here's basically the smallest recurrent neural net that we can think of. So let me try to just clarify or highlight what are the ingredients of this neural net that we're looking at here, right? So I kind of shrunk it and threw away all unnecessary parts. So what it consists of here is, right, we have still input features that are coming in at step t. We still have an output neuron for what we produce at step t, the output of our prediction. And then I haven't said exactly how yet, but the state that we have at the end of step t is forwarded to the next step. And I'll say how in just a second. So this very simple architecture just has a single hidden layer. Right? We can always generalize this to more. So just as in standard fully connected feed-forward neural nets, we'll describe all the weights on these connections between the input features in step t and the hidden units by a matrix U, which is the input to hidden weight matrix. So again, watch the videos on standard feed-forward neural net if you're not familiar with this notation. We'll also have a bias vector here for the hidden neurons. We call it B. Again, this is completely standard. Then we also have to produce our output also as completely normal feed-forward neural nets. We'll have a weight matrix V given the hidden to output weight matrix, all the weights on the connections between the hidden neurons and the output neurons. There could be more than one. If we have, for instance, classification into K classes, there could be K output neurons, right? So we have a matrix V here. Everything now is still standard. We have an output bias vector as well, C. These are all the ingredients of a standard feed-forward neural net. Now, the new ingredient is that we also have this hidden-to-hidden weight matrix, right? So this is, in some sense, responsible for I have these hidden neurons at the end of a computation step, and we want to forward it to the next step, and it's going to pass through this matrix W, as I'll show you in just a second. So finally, these neurons in the hidden layer here, they have an activation function. And this activation function, for reasons that we'll talk about in the next video, is most typically the tanh function. So let me just remind everyone, what is the tanh function? Right, so let's see what it is. So first of all, the sigmoid function, if you saw logistic regression, you remember it as this special function that lies between 0 and 1. It takes values close to 0 for very negative inputs. It takes values very close to 1 for very positive inputs, and we used it in logistic regression to predict values between 0 and 1, like probabilities, for instance, of being in a particular class or for a particular event to happen that we're trying to predict. And basically, this function is defined as 1 over 1 plus e to the minus z, and it has this S-like shape, right? In some sense, the idea is that this neuron fires if you have a large set as input. This was the sigmoid function. And then this hyperbolic tangent, or tanh, as we pronounce it, is basically defined as taking the sigmoid, multiplying with 2 to make it taller, to stretch it, and subtract 1 off to shift it down, so that this is a function that lies between -1 and 1, right? So it's just a scaled, shifted sigmoid function. So it has output values that lie in the interval from -1 to 1. So this is the hyperbolic tanh. And this is the function that we're going to use as activation. And in the next video, we'll talk a bit about why this is a good choice of activation function for recurrent neural nets. And we'll also discuss briefly why perhaps neurons such as ReLU, the rectified linear unit, might not be as appropriate for recurrent neural nets as the tanh function is. Okay, but let's get back to that later. So we have, this is basically the setup of our little recurrent neural net, right? We have these tanh activation functions here at the hidden layer. We have weight matrices, we have bias vectors. And let's see now, if we have our feature vectors, x1, x2, x3, and so forth, how do we process it, right? So first of all, let me just say what the shapes are of all these vectors and matrices. Let's say we have D input features per time step. We have H hidden neurons and O output neurons. Right, then the bias vector for the output is just a 1 by O. It's just a row vector, as we're used to. V here is the matrix, right, that you get that you use to get from the outputs of the hidden neurons to the output here. So it's an H by O matrix. The input to hidden neurons weight matrix is D by H. And the weight matrix here from hidden to hidden is an H by H matrix. Finally, right, the bias here for the hidden neurons is a 1 by H matrix, a vector, sorry. Okay, so just with this notation, let's be a little bit more formal about how you process the sequence x1, x2, x3 through such a recurrent neural net. Right, so for the step 1, right, I guess we need to feed in some state from step t-1, right, some step 0. And as we talked about, I guess we have some standard initialization here. Here we have 3 hidden units, and so we'll just make it 3 long. We'll make it H long, this first, I guess, state coming from the previous step. So we'll just make it all zeros just to have some arbitrary but fixed choice. And now comes the actual computation, right? So what we do first is we want to compute the outputs of the hidden neurons here after step 1. Right, so what we do is we feed in, so we have this x1 feature vector here, we feed it into the neural net, and we pass it through these weights here. So this happens by multiplying it from the left onto the U matrix, right? So this is just like a standard feed-forward, fully connected neural net. We take our feature vector as a row vector, multiply it with U. And now the interesting point, a new twist to it, is that we also get the state from the previous step. Here, the state is just the all zeros vector, but we take it and multiply it on the left with the W matrix, right? So this is a special matrix here that's used for taking the output of the hidden layer from the previous step and forwarding it into the next layer. So basically, one can think of it as, I guess there was some connections here between the hidden layer and these inputs that are coming from the previous hidden layer. So we multiply it from the left onto W, and finally we add the bias vector and apply the activation function tanh. Okay, and then we need to produce the output of step 1, and we do this just as in a completely standard feed-forward neural net. We take this row vector that gives the outputs of all the hidden neurons, we multiply it from the left onto the V matrix, add the output bias C, and this is our output. Now, this is in particular for regression type problems where we use identity activation on the output. Of course, you could also use other activations. Perhaps you could have applied a softmax function on this if we had K output neurons and we're doing classification into K classes. Maybe if this was a logistic regression type problem, maybe we applied a sigmoid function or whatever. Right, so there are different choices. You could put activation on the output, but here we'll just keep it simple. We're doing regression. We don't have any activation on the output. Okay, so this was like processing step 1. And if we now move on to step 2, the important point is that now we have the hidden neurons from the previous step in this H1 vector, right? That's the output of the hidden neurons in the previous step. And these are the ones that we now feed into the next step, right? So we get our X2 feature vector from the input, and multiply it on the left onto U, like a standard feed-forward neural net. And we take our hidden output from the previous step, H1 here, and multiply it from the left onto W. And finally, we add our B and apply our activation tanh. And then we get our output of step 2, the hidden layers of step 2. Finally, to get the actual output of step 2, right, we take our hidden output from step 2, multiply from the left onto V, add the C, just as in a standard feed-forward neural net. Move on to step 3. We feed in the step 3 feature vector multiplied with U. We feed in the step 2 hidden output multiplied with W, add the B, and apply our activation. Right. So this is how this recurrent step where we feed in state from the previous step into the next one. Okay, good. So just to keep the notation and the figures a little bit simpler for the rest of this video, let's just throw away the biases. Let's just pretend they're not there. Of course, they are there if you actually implement it. You want to have these biases, but just to keep the math and notation a little bit cleaner, let's just throw them away from here on, right? So let's just get rid of all these biases, right? So it cleans up things a little bit. Okay, so let's have a closer look at this. So basically, the step T functionality is just to compute the output of the hidden neurons in step T. We take the input from step T, the XT feature vector multiplied with U, add the hidden output from the previous layer times W and apply the activation. And to get the output, we take these hidden outputs and multiply it with V. Right? These are the general steps of the computation. Okay. Now to train it, right, we of course need a loss function that we can minimize. So what we're going to use is we're going to, again, just work with a standard loss function, a pointwise loss that we can kind of apply to an output prediction Y prime and an actual label Y. And this loss function could be all the standard ones like least squared loss. It could be, if it's a prediction with K classes, could be the cross entropy loss function where we probably want to apply a softmax here to the output first and so on. Or to just take any of the loss functions we've seen before. And now if I pass a sequence through this recurrent neural net, I do all the steps that basically I do a step for every single step in the sequence. The sequence has labels Y1, Y2, YT, and so forth, features X1, X2, and so on. Then the loss that we incur from processing this sequence, let's say the sequence has length capital T, then we just sum over all the outputs that we produce. Right, so every single step produces an output when we process that step. We take the output OT, so this is the output of this recurrent neural net on the step T of processing the sequence, and we just apply this loss on this prediction and the true label in step T, right? So nothing surprising there. And finally, if our training data consists of a whole bunch of sequences, n different training sequences, then our loss is just the mean or the average loss over all these sequences, right? Just as we normally have when we have multiple training points, right? So we just average this loss on all the different sequences. Okay. One could also consider normalization terms that tries to normalize by the length of these sequences. Doesn't matter, right? For at least for the function to minimize one of them, you minimize the other. Maybe for numeric stability, maybe you would like to do something here, but let's ignore that for now. Okay, so the question is really, how can we train our neural nets, right? So we need to change our parameters U, V, and W to minimize this loss on the training data, right? So this is what we would like to be able to do. Okay, and of course, the algorithm that we're going to use is the standard off-the-shelf mini-batch stochastic gradient descent that we also saw for minimizing losses when we have standard neural networks, right? Because this algorithm, it only needs gradients in order to run this algorithm. Basically, the gradient of the loss function with respect to all the weights or parameters of the neural net, right? So it doesn't require much in order for you to actually run this optimization algorithm. Of course, right, a similar concern as we had for standard neural nets is that the loss of a neural net, when we unfold it all, it's not a convex loss function of the parameters. So there can be multiple local minima. And when we run stochastic gradient descent, we might end up in a local minima. But still, like with standard neural nets, we're just gonna ignore this issue. And in practice, these local minima are just good enough, right? So this is all the same as when we did the standard neural nets. Okay, so here's the template for a stochastic gradient descent in the setup of these recurrent neural nets. So recall again, right, that the error that we're trying to minimize is this in-sample error, which is the average over all training sequences that we have. And for every training sequence, right, we sum over all the different outputs on the sequence. So the sequence S here, SI, consists of a whole tuple, a list of feature vectors. And each of these, this xi should be superscripted with a t as well, right? So this is the tth feature vector in the ith input sequence. We look at the output here in step t. I guess we could also write the notation like this. So the tth output when processing this this whole sequence si that has a whole bunch of feature vectors, one for every step. So basically, we just look at the tth output and we compare it to the tth label. And we measure this loss, right? This is what we want to minimize. And mini-batch stochastic gradient descent tells us to initialize these weight matrices somehow, right? Maybe just an arbitrary, maybe it's not the best choice, but just randomly normal distributed mean zero and variance 1 is some choice. This is not necessarily the best choice, but just to find some way of initializing them. And then we repeat this loop. While there's more time, we execute what's called an epoch, right? Where we permute all the training data. Each of these x1, y1 is now a sequence, right? So each of these unfolds into a whole bunch of sequence vectors, permute them randomly, run through them in batches of B. So we gather the next B data items and next B sequences. And now we kind of pretend that this is our whole training data, and then we just compute the gradient of this loss function up here as if only those B items were our training data, compute the gradient with respect to U, V, and W, right? So we get all these partial derivatives with respect to all the entries of the matrices U, V, and W of this loss function. And then we take a small step in the negative direction of the gradient, right? So what we need to be able to compute to execute this stochastic gradient descent is we need to be able to compute these gradient, right? The partial derivatives of this loss function with respect to all the parameters inside the U, V, and W matrix. Right. So again, all of this stochastic gradient descent has been covered before in these videos on training neural nets, right? So go watch them again if you've forgotten. Okay. And the algorithm that we're going to use to compute these gradients is the backpropagation algorithm that we also saw in previous videos. And again, I encourage you to watch these videos again if you've forgotten all about it. But backprop is an efficient algorithm for computing these gradients of arbitrary computations, right? So in general, if we have a so-called computation graph, we can compute these gradients, right? So what we need to do is now take these recurrent neural net structures and convert them into a computation graph. And for convenience, we'll use these vectorized computation graphs that were also covered in one of the previous videos on training standard neural nets, right? So go watch that again if you've forgotten. Okay, so let's try to see what does the computation graph look like corresponding to such a recurrent neural net, right? So the recurrent neural net had this special structure that we run for multiple steps. And in step T, right, we take the tth input feature vector multiplied with U. We take the output of the hidden layer in the previous step, the ht minus 1, we multiply with v, we sum them and apply a tanh, and we compute an output here. Let's try to look at what does this computation graph look like. All right, so recall that these computation graphs, they have an input for each of the variables that occur in the computation, right? And these variables here may be both vectors and matrices, right? So in general, right, the inputs are the v, u, and w matrices, is the feature vectors x1, x2, and so on. And then also we have the special h0, which is the initial dummy initialization, if you will, of the hidden layers. Okay, so if we just follow these computation steps, let's see what happens, right? So we see that first of all, right, we do a vector matrix multiplication between the feature vectors in step 1 and the U matrix, right? So this node here is a vector matrix product that it computes. We also multiply the ht minus 1, so that's the h0 with the w in a vector matrix product. We add them up with a sum, and we apply tanh on the output here. This is now our h1, if you will. This is, if we call it h1, this node here, in the computation step. Then to compute the output, right, we take this h1 and do a vector matrix product with the v matrix, and this is our O1 output. Okay, then we move on to step 2 of the computation. Right, so if we unfold all of this, what happens is we start by taking the x2 feature vector and multiplying it with u. So this is a vector matrix product here. Now we take also the h1 vector, which we have up here in the computation graph, and multiply it with v. So this is the vector matrix product here. And now we sum them up, these two vectors, and we apply the hyperbolic tanh and up here to get the h2 output. And we now multiply this with v in a vector matrix product to get the O2 output, and so on, right? So this is, you can just unfold all of these steps into a very large computation graph. It comes very deep, right? Because the output h1 here is then fed into the next part of the computation, and so on, right? But basically we just unfold it to a computation graph. And now just to maybe look at the overall structure of this computation graph, we're going to try and simplify this figure a little bit. So basically what we can see here in this triangle is that this is basically the computation of ht for a single step, or h1 in this case, right? So in comes the input feature vectors w and u, and the hidden output from the previous step, and out comes the hidden layer, the hidden output from a step here. So let's try to, if we just visualize this, I'll zoom out a little bit. What we have is that we get w and u comes in, the hidden output from, I guess in this case, step 0 comes in, and the step 1 feature vector comes in, and then there's some computation graph here that outputs h1. Right, then what we did with this is that we also now, to compute the output, we feed in the v matrix, and there's some computation here, in this case, just a product, and out comes O1, the output from step 1. Now in step 2, right, I guess in comes again h1, w, u, and x2 goes into a computation, and out comes h2. From h2, we feed in v and h2 to compute the second output, O2. And for step 3, we again feed in w, u, the x3 feature vector. We take the output, or the hidden h2, feed it in, and out comes h3. We compute, we take v as input, we compute the third output, and so on, right? This is really, if we try to unfold this computation graph, where we zoom out a little bit, this is the general structure of the computation graph. Okay, so a complicated setup, but where this v, u, and w is fed into a computation step in every single step, and then these hidden outputs are fed forward into this computation graph. Now, of course, when we want to do gradient descent, right, it's really the loss function that we're minimizing, so we also need to include the loss function in this computation graph, right, for the purpose of doing backpropagation. So recall again that the loss on a single sequence is the sum over all the individual steps of the sequence of the loss applied to the output in the step t and the label in step t. So we want to add this to the computation graph as well, right? So for step 1, we have another input. So this is actually one of the input parameters is the y1 label. it goes together with the O1 output into a small computation here where we compute the loss function, right? So there's some way of computing the loss, and this is the contribution to the loss here. And we do this for step 2 as well, right? The step 2 output is combined also with the step 2 label to compute the contribution to the loss here. So there's some computation of the loss. Similarly for step 3. And finally, we add it all up in this definition of the total loss. It's the sum of all of this. And this is the final output. This output of this whole computation graph is what we're trying to minimize. And this is where we want to compute gradients of this function with respect to our v, w, and u. And we want to compute it at the current set of values, right? So we can do gradient descent. Okay. So how can we compute these gradients, right? And this is something that we also looked at previously. So in previous videos on backpropagation for neural nets in particular, we had a video on doing it for vectorized computation graphs. So basically the idea is if I have such a computation graph, now here I'm taking another example just to make it a little bit smaller, right? So it's a general computation graph where we have vector and matrix variables. We have nodes that compute vector matrix products, as we saw before, right? We can sum up vectors in this case, and we can apply entry-wise activation functions. So the general idea, right, to compute these gradients is that we name all the nodes, and we do the so-called forward pass, right? So let me just run through this very small example, right? So in here, we have some variables. We call one X. We have a W1, a W2, a B1, and a B2. These are matrices and vectors. And we want to compute the gradients of this function, the whole function f here, with respect to these different variables. And we just want to evaluate, we don't want a formula for this gradient, we just want to evaluate it at the current set of parameters. So what we should do is that we should do first the so-called forward pass, right? So we send all these variables forward along the edges of this computation graph, and then we just execute the computations, right? So here we want to do a vector matrix product, this vector here with this matrix. If you do the calculations, you get the 4,3 vector. Now we want to add it with the 1,1 vector, so we get the 5,4 vector. We have some concrete activation in mind here. Maybe this activation is the squaring. So if an entry-wise squaring, right? So if a vector A comes in, we entry-wise square all the entries. This could be the computation here. So if I do that, I square the 5, I square the 4, I get a new output here. This is a vector matrix product. So if I do the vector matrix product, I get 9. This is a summation. So I add the 9 and the -2, I get a 7. And maybe here I have an identity activation at the output and I get a 7, right? So this is general. We just do the forward pass, just evaluate it. This is exactly what we could do for the recurrent neural nets, right? We can just evaluate the whole neural net in this feed-forward fashion, nothing special there. The hard part is, of course, we have this backwards pass where we compute all the gradients. Like, so in the beginning, right, we said we basically be computing a gradient on all of these edges, if you remember. So we always start by just putting a 1 on this output edge. And also the neuron that, not the neuron, the steps that are going directly into the output node here. We also do those directly. So we see here, what is the f function? The f function is the identity. So f is just equal to e. So the partial derivative of e with respect to e, it's just 1. So we also put a 1 on this edge. Now we want to move backwards. We want to compute the partial derivative of f with respect to d. So we use the chain rule. So we say this is the partial derivative of f with respect to e times the partial derivative of e with respect to d. F with respect to e, we already computed, is on this edge up here. It's the 1. So we put in the 1. And what is the e function? Well, the e function is the sum of d and the b2 variable, right? So it's not a b squared, it's a b2. So it's the sum of d and b2. And we want to take partial derivative with respect to d. We see that this is 1. So it's 1 times 1, it's 1, right? So we get this 1 here. Right, so we can keep doing the backwards pass. So now we want to compute along this edge here. We want to do the partial derivative of f with respect to b2. Chain rule, this is the partial derivative of f with respect to e times e with respect to b2. F with respect to e, we already computed, it's a 1. And the e expression is d plus b2. And if we do with respect to b2, this is 1. And so we get a 1 here on this edge as well. All right, we continue. Let's try to do f with respect to c. So chain rule tells us it's f with respect to d, right? So this is what we have on this edge. d with respect to c. So this is a 1. D with respect to c. So what is the d function here, right? D is a product between c and w2. The problem here is that c is not a scalar, right? So this is not really, at least with standard partial derivatives, this expression here is not well defined, right? So we cannot really, how do we take partial derivatives with respect to c when c is not a scalar, right? And as we saw earlier, you can actually still use this expression for the chain rule. This is still a valid expression, only that this partial derivative d with respect to c is not really a partial derivative, but it's the matrix of derivatives that we talked about. So matrix of derivatives is really, in the standard terminology, is the Jacobian. So let us just remind ourselves what this is, right? So this matrix of derivatives, or typically called the Jacobian, is defined as follows, right? So if I have a function that takes multiple variables in and produces multiple outputs, so L, right, is really a function that produces k outputs, L1 up to Lk. This is a function of d input variables, x1 to xd. So it's a function from Rd to Rk. And if we assume that each of these functions is a differentiable function, and the matrix of derivatives is just the matrix, it has one row for every output. So it has k rows. So one column for every input. And in entry I, j is just the partial derivative of the ith output function Li with respect to the jth variable xj. Right, so this is just what the matrix of derivatives is. Okay, so we saw also in previous lectures, and I'm not going to repeat this, if we use this rule or these Jacobians, and we look through all these different nodes that appear in these vectorized computation graphs, we did it painstakingly. We did all the details. We computed what you should actually do when you're processing each of these different nodes. And so we're not going to rederive these formulas. We're just going to remind you what you should do, and then you can just use it. So in particular, if we have these nodes here, these AB nodes where we compute a vector matrix product, let's say we already computed a partial derivative along this path from the output of the function and down to this edge here. So basically this is a matrix that's sitting there. What you have to do in these nodes is very simple. There's just two things to remember. So if we want to compute the partial derivative of f with respect to a, so we're going in this direction, we want to compute what's on this edge here of the computation graph doing backpropagation. What we should take is just a partial derivative of f with respect to c. So this is what we already have written on this edge here. So we just take whatever is on this output edge, and then we just need to multiply it with b transpose, right? And b we have from the forward pass. So it's written on this edge already in green. Right, so this is a very simple step. So if we take this 10, minus 8, multiplying it with b transpose here, we get 12, minus 8, right? So this is a simple rule to remember. And if we're going the other direction, if we want to compute the partial derivative of f with respect to b, so we want to know what's on this edge, only thing we have to do is we have to take the a vector here, we transpose it and multiply it with what's on this edge, the partial derivative of f with respect to c. Right, so this is very equivalent to the standard. If we have a standard rule, if this was a multiplication of scalars a times b, if we take the derivative with respect to a, we get b. If we take the derivative with respect to b, we get a. This is similarly here, only that we transpose these two. We transpose the b, we transpose the a. Otherwise, it's the same. Right. So very simple rules. And if we do it in this case, right, if we take a transpose here, a is the 2, 1 vector, we transpose it, multiplying out 10, minus 8, we get this. Right, so this is just one rule to remember. If we have a summation, if C is a summation of two variables, the easy thing to remember is that basically, if you do the chain rule, you have to multiply what you have up here with the identity matrix. So we just copy it down into both of them, right? So it's very easy to remember. This is, I guess, similar to addition of scalars, where if you have a summation of a plus b and you take partial derivative with respect to a, you get 1. Partial derivative with respect to b, you get 1. And if you multiply that onto what's coming here from above, you just keep it as it is. Finally, if we have an entry-wise activation function in one of these nodes of the computation graph, what you have to remember is just that you take this partial derivative that you already computed, f with respect to c is on this edge, and then you multiply it from the right onto this diagonal matrix, where you have this activation function, right? So it's a function that works on just a single variable, right? You're applying it entry-wise. All you have to do is you have just to take the derivative of this single variable function, and then you just apply it on what comes from the forward pass. In particular, in each entry here, you just have whatever is on each of the entries of this vector here. Right, so this is the applied to 4, and the second entry is this partial derivative, the derivative applied to 3. Okay, so just to do the example here, right? Maybe this activation function takes in an x, in entry-wise, it computes e to the x squared, right? So if you do the derivative of this function, you get e to the x squared times 2x just by the chain rule. And what we can do now is, if we want to compute what should be on this edge during backpropagation, right? The formula says take whatever you have from above, 10, -8, multiplying it with a diagonal matrix, where we just need to feed in 4 in this derivative of here. So e to the 4 squared, that's e to the 16th, times 2 times 4, that's 8. And similarly here, we feed in 3. So we get e to the 3 squared, that's e to the 9, times 2 times 3, that's a 6. And this is all we're doing. And so these are the rules to remember. And these actually covers all the different computation nodes that we had in the graph that we get from unfolding the recurrent neural net, right? So now we can just apply these rules and compute all these partial derivatives, right? And this is what we get if we just complete the steps of this computation graph that we saw before. And if you want to see the details, just go back and watch the previous video. This is pretty tedious to do by hand, but it's doable, and in code you can easily do it. In particular, now we have this giant computation graph, but if we unfolded all of these gray triangles here, all they're doing is vector matrix products and summations and activation functions that work on individual nodes, right? So you can actually just do it on this graph. One thing to be aware of that's in particular occurs very often in these recurrent neural nets is that some of these variables, are used in multiple places, right? In particular, v, u, and w are used in every time step. And also these hidden outputs here, h1, h2, h3, they're forwarded both to the computation of the loss here, the output step 1. They're also forwarded into the next step of the computation, right? So variables are reused. And when variables are reused, we just need to remember we have this special rule from backpropagation. If we have a node somewhere down the computation graph here, this node C, and so somehow we're computing a function f that has a single output, then if we're running backpropagation using this algorithm that we described before, then on each of these edges, we'll compute a partial derivative, right, f with respect to c. Right? These might be vectors, for instance, if it's a vectorized computation graph, but we'll compute one along each of these edges when we do the backwards pass. Now, the important rule to remember is just when I'm continuing my backwards pass below this node here, maybe this node is also has some incoming edges, then I just need to sum up all of these partial derivatives to be used further down the computation graph, right? This is also the case on the u, v, and w. If you remember these parameters, they're sitting as basically inputs to the computation graph, and they're used in many places. You'll get, I guess you'll get these partial derivatives on all of those edges, and you just have to sum them up, right? This is all that we need to do. We have to add them up in the computation. Okay. And so PyTorch, right, and this is all very tedious to do by hand, but PyTorch does this for you automatically. It automates the backwards pass. All you have to do is really to implement the forward pass of the computation, right? So you just have to just describe or do the computation steps that a recurrent neural net is doing, and then it'll automatically do all of this for you, right? So this is very convenient. But I think it's also nice to know how does it work underneath the hood, and this is what we just saw. So stochastic gradient descent is the algorithm that we can use with recurrent neural nets. All we have to do is just run all of these iterations where we do these little mini batches where we take B different sequences and we compute all these gradients of this loss function. We do basically unfold this entire computation graph that we just saw, which includes the loss. and then we just do backpropagation to compute all the gradients. Right. So this is how we train these recurrent neural nets. And in this last video on recurrent neural nets that is coming up, we will discuss different things to keep in mind when working with these recurrent neural nets.